Good afternoon, everybody. Thank you for the invitation today. I'm Max. I started my studies at the BOKU in 2012, did all the way till the end of my PhD here, finishing off on automotive parts, as I already said, and mainly focusing on wood. Right now, I'm a postdoc at Professor Konrad's working group at the Institute of Wood Technology and Renewable Resources, and we are dealing with structural wood composites for building construction. Today, on behalf of my co-authors and myself, I would like to talk about climate-resilient automotive parts. So we all know who this is, James Bond. Since 1962, he's saving the world from bad guys, looking dapper and using a variety of different gadgets. So one of his main gadgets is his car. And while he stayed in shape throughout the years, his cars did certainly not. Taking a look at one of the most favorite ones, the Aston Martin DB5 and the Aston Martin DB11, we can see one very important thing. I'm not sure if 20 seconds is working on, already at 30 or something? No, okay. Sorry. Taking a look at one of the most prominent ones, the Aston Martin DB5 and the Aston Martin DB11, we can see a weight increase of around 30%. So from the mid-60s to around the early 2000s, we have a gain of almost 30% in weight. So why do I tell you this, would be the question now. The reason for that is that 25% of a car's fuel consumption is caused by its weight. This is the second biggest contributor after the car's powertrain. This leads to a very high emissions of different cars. So 007 may be saving the world from bad guys, but he is not saving the climate. This relation is also true for average Joe and Jane's car. Taking a look at the Golf from Volkswagen, we can see its weight more than doubled within the last 40 years or within the last 50 years since its first introduction. This has led to the fact that around 12% of the global greenhouse gas emissions are only caused by the road transport sector. And this only comes from the consumption of fuel. So the building of the cars is not included here. So now we can think about what to do in order to reduce this 12%. An obvious answer would be use public transport and electrify the cars. On the other hand, we can also try to build lighter cars again. And this has brought up a field called lightweight construction in recent decades. The goal of this field is to use lighter materials which still have the same mechanical performance, like elasticity, for example. And it should be lighter than metals, which are the most commonly used materials in the previous years. So far, it is really important to note that not really a natural material has found its way back into the automotive industry. But wood, or the top levels of wood, would serve a great deal in this regard because it has even lower densities and still achieves similar mechanical performance. But there are a few key differences between wood and metals, for example. And therefore, it can be that when a car expert and a wood expert talk to each other, that there are some misunderstandings happening. And here, the vision of my dissertation and my colleagues is to bring the car expert and the wood expert closer together again. And therefore, we looked at two key differences. And the first one is the directionality of the wood's mechanical properties, also called anisotropy. So in a longitudinal direction, we have the highest performance, let's say 100%. Perpendicular to it, radial or tangential direction, we only have 10%. So the fiber orientation and fiber angle is a really important factor when using wood in the automotive industry. In order to characterize that, we teamed up with Professor Josef Kekkes from Montano e Leoben, and we used X-rays in order to see through the samples we have and gain insight on the fiber orientation. The method is called X-ray scattering, and it works as follows. You take a sample and you send an X-ray beam through the sample. Depending on the orientation of the crystalline cellulose, so the fibers basically, we can bent, or the X-ray beam gets bent according to this orientation, and this bending angle can be recorded on a detector afterwards. Additionally, we need some mathematical witchcraft. Don't regard the formulas. It basically gives us a relation between the material strength and the fiber angle the material has. So the lines are important in this regard. And now, when we print the angles that we measured with wide-angle X-ray scattering against this failure criteria, this is the name for them, we were able to predict the strength of thin wood sheets that were our samples with an accuracy of up to 89%. This is pretty darn good for a natural material, actually. So now we were able to describe anisotropy. The second factor we looked at was the uniqueness of wood. So basically the variation or variability of its mechanical properties. Compared to steel, for example, we have a very high variability, and steel or metals have a very low variability. In order to overcome that, we teamed up with colleagues from the TU Graz, and we got inspired by nature from a different side. We looked at mollusk shells. The structure of these mollusk shells are really special and are able to decrease variability on the one hand and also increase the tolerance of wood against damage. In other words, make it tougher. Why is that? The structure is called crossed lamellar structure and is made out of different macroscopic layers, as you can see on the middle of the picture, and also of different suborder lamellas, as you can see on the side. And this complex hierarchical structure basically creates a predefined crack path when the material fails. So when we load the material till it breaks along the interfaces we have created with our multi-material structure, as you can see on the dashed line. Therefore, the material breaks predictably and decreases variability significantly compared to solid wood, as you can see here. Additionally, taking another composite made out of wood, plywood, I think you all know that, we were able to increase the toughness significantly as well. Therefore, we were able to also answer the car expert's question about the variation of the material. These are two key differences we looked at, but there are still a lot of open questions out there on our way to all-out bio-based cars. However, we are already on answering that questions, and with that I would like to conclude my presentation for today, and I'm open for any question that may have come up now. Thank you very much.